today's session. Today we would be understanding the concept of ocean temperature. Before we start with ocean temperature, we'll be understanding few basic concepts that we'll require to see how the temperature of the ocean changes with the depth. So the first concept we would be talking about is transfer of heat. Now heat transfer broadly takes place by three ways. First is radiation, the next is conduction, and the last is convection. Now some of you might be questioning, why is this diagram here and how is it related to the three concepts? So let's try to understand what is in the picture. So there is a picture where teacher is taking a class and there are two rows of students who are sitting. Now the student who is in the last row, for the teacher's perspective, is this, and this is student who wants to transfer one of his books to the teacher. How that boy can do this? There are three ways of doing this. Either this boy can take this book and throw it, okay? So that's a kind of radiation. So what is happening? Book, which we can consider as energy, is moving from this from the disk of this child to the teacher, okay? And that is a direct movement, and that is known as radiation. The best example is sun rays that touch our surface of the earth or the ocean. Okay, so that is by means of radiation. The next is conduction. What happens in conduction is, this boy would transfer the book to the girl sitting next to the boy, and the girl will hand over the book to the teacher. So again what is happening is, the energy is moving, okay, and it is from one to the next. So it's a kind of, it goes into a linear fashion. A best example of conduction is, if you are trying to heat a metal rod, if you will heat the first portion, slowly and gradually the heat will dissipate and the whole rod would become hot. The next is convection. What happens in convection is, this child would take the book, stand and go to the teacher, hand over the book to the teacher. The teacher in turn, when she has completed reading the book, or she has completed reading the section of it, she will go back and return the book to the child. So what is happening here is, here both particle and energy is moving. So this boy, who is considered as an entity, is moving, and none of the other forces, none of the other heat transfer mechanisms did the particle move. Okay, so the only particle and energy move in convection. And the best example of convection is, if you are heating water in a pot, what happens is, you have a water on the flame. So the lower section of the water gets heated, and this whole layer slowly and gradually moves up, and the cold layer comes down. So this is a kind of convection current that flows in. So these are the three fundamental concepts that we try to understand for heat transfer. Now once we are done with heat transfer, we will try to understand how sun rays penetrate into the surface. So when there is a sun rays coming onto the surface, it broadly comes under three waves. First is the visible spectrum. You have the infrared spectrum, and finally the ultraviolet spectrum. So this infrared spectrum, which is shown in red color here, has longest wavelengths in contrast to the ultraviolet and the visible spectrum. Now thus ultraviolet and this visible spectrum, despite of having high energy, constitute shorter wavelengths, and as a result, these shorter wavelengths can penetrate deeper. So they have deeper penetration contrast to infrared waves, which are long wavelength, and they usually touch the surface. Okay. So to understand how temperature changes in the ocean in the very first layer, so you have this diagram for how the temperature changes in the ocean, but right now we would be covering only the topmost or the surface layer. So the layer marked here in green, this section is the surface layer of the ocean, and this layer receives infrared radiations, okay, and the heating here is mainly by the sun rays that are falling onto this region, okay. Now, so the temperature in this upper few meters, or what we call the surface layer, is governed by the insolation or the incoming solar radiations that hit to the surface of the ocean. Now, to understand the remaining layers, we will first discuss some of the concepts. So, the first concept here is, in this diagram, as you can see, we have marked three things. Okay. So, you have temperature that's marked onto the bottom. So, you have temperatures in degrees Celsius. This region, you have the salinity, and this side, you have the density. Now, temperature is mentioned in degrees Celsius. You have density, which is given in weight per cubic meters, and finally you have salinity, which is given in PSU. Now, PSU is a practical salinity unit where we consider that on an average the seawater is at around 15 degrees Celsius. Okay, and with this 15 degrees Celsius of seawater, you have a solution. It is equivalent to a solution of KCl, which is having 32.4 grams of KCl in 1 kilogram of the total solutions. So we consider the average salinity as 35 PSUs for the ocean. Okay. So in this diagram, you have the average salinity is 35 PSU for the oceans. Okay. There is another unit for measuring salinity, that's part per thousand. That is again considered as one of the units for salinity. Now, in this diagram, as we can see, you have density which increases proportionally to the salinity. Okay. So therefore, we can say salinity affects the density or governs the density of the ocean water, and there is a directly proportional relationship between the salinity and the density. Now this curve shows a curve for normal water with zero salinity. For this water, you would have a maximum density at 4 degrees. Okay, and then as you can see, you have density which increases till here. Here you have the maximum density, and then you have a decline in density on this isohaline curve. So now we'll understand why does ice floats. We say that water has maximum density at 4 degrees Celsius. This implies that water below 4 degrees Celsius would become lighter. So the 4 degree, you have maximum density. Okay. That means this 4 degree water would tend to subside down. So this is the ocean body. So this would be your 4 degree water, which is maximum density, would subside down. And after 4 degrees, as you decrease the temperature, the density tends to change. So you have 4 degrees maximum density. So 3 degrees would be lighter than this. So you have 3 degrees, you have 2 degrees, you have 1 degree which is further lighter, and finally you have the 0 degree which is the ice, and this floats on the surface of the ocean body. So this is the reason why we say that ice floats on the surface of the water body. The main reason is water has a typical characteristics of having maximum density at 4 degrees Celsius. If it was any other metal besides water, what would happen is, as you would increase the temperature, there would be change in density, and rather than floating, it would kind to settle down. Okay, so that's why we can understand why ice floats. Now, this was the first fundamental concept we have tried to capture here. Now, when we try to understand this concept, let's try to move back to our slide. So, this change in temperature is affected by few things that we have understood here. First is the salinity. Next is the radiations. The third is the waves and the winds. Now, as we already talked about the surface layer, which is this. Okay, this surface layer is affected by the radiation, that's the incoming solar radiations or the infrared radiations that touch the surface, and therefore this region becomes hot. As we can see, there are two lines here. One is this line, which is the line for summers, and this is the line for winters. So as we see, this radiation or incoming solar radiation changes in winters. You have less incoming solar radiation, so this line will shift, or this curve will shift here. Okay. The next is the mixed layer. This mixed layer extends to around 200 meters, up to 200 meters, and this layer is mainly affected by the waves and the wind currents that flows here. Now, this is the layer which captures the most of the sediment flow. So these sediments won't be able to percolate below this layer. As we can see in this graph, there is a drastic change in the temperature in this zone, and this zone is known as the thermocline, that extends from around 200 meters to 1000 meters. And this is a zone of rapid temperature change. We call it thermocline. Cline itself means rapid change. So I can use various phrases here. If I use halocline, halo means salinity. So rapid change in salinity would be halocline. If I use pinicocline, that means there is a rapid change in density. Okay. Now we would be understanding how the density and the freezing temperature is affected by changes in temperature and salinity. So let's understand the same diagram that we previously discussed. The one we discussed included only the fresh water, that is the water with zero salinity. In this diagram, what we are trying to do is, we are trying to create isohalines where we are trying to change the salinity from 5 PSU, 0 PSU, 5 PSU to 45 PSU. So let me take any temperature, say at 20 degrees Celsius. Okay. So this is the temperature I am considering. What is happening at 20 degrees Celsius is, when there is a significant change in the salinity, there would be a proportional change in the density. Okay. Therefore, it implies a change in salinity directly affects the change in density. And in this curve, you can see there is a line of maximum density. So what we can see here is, as you are increasing the salinity, so as we are going higher in the salinity, the maximum density of the water is decreasing. That means, as there is more salinity, the density of the water is increasing. So we can say the maximum density curve which we say for pure water it is 4 degrees Celsius, would try to slowly come down with increase in the levels of salinity. So in this diagram we can see there is a linear decline in both temperature of maximum density and the freezing temperature. Usually we consider the average ocean water at around 35 PSUs, that's here. So at 35 PSUs, if I draw kind of lines here, I can say a water which is at 35 PSU would kind of freeze at minus 1.8 degrees Celsius nearly. That was on this curve, so you have minus 2.5 here, so above that you would have around minus 2. Okay, so this would be the region or the freezing point of a salt water which has an average salinity of 35 PSU. Similarly, we can see this is the line of maximum density, and this line of maximum density is constantly decreasing linearly with the freezing temperature. So let's move back to the previous slide. Here we can understand. So you have the temperature that is declining here, and the maximum density curve which is again declining with the increase in salinity. As this increase in salinity leads to higher density. Okay. So these are the things we are trying to understand by means of these curves. So once we understand this curve, another important term here is to understand the concept of brine rejection. Now what happens basically is in polar areas you have ice that freezes. Okay. Now what is happening when the ice is freezing? When there is ice that is freezing, you have molecules of brine that are trapped into it. And that trapping of molecules is usually in the form of honeycomb structure. You have brine, and this brine is a very high concentration of salt in a solution. So you have high concentration of salt in any given solution. So what happens is when you have ice, okay, so ice freezes at 0 degree because it's fresh water. So you have this complete layer of ice that is frozen at 0 degrees Celsius because it's fresh water. But this brine, due to increased salinity, the density increases and the freezing temperature decreases. So you will have pockets of brine within this ice, and these pockets would remain in liquid state. So they would be in kind of liquid state because of the salinity, they have lower freezing temperature, and the freezing temperature here is 0 degrees. So they would stay, they would need around a temperature of minus 2 or more or less to freeze, and here they would remain in the liquid state. So what would happen is this brine which is present in the pockets here would slowly and gradually try to percolate down. So you have this top layer of the ocean, okay, and from this top layer of the ocean you would have brine which would be percolating down, or the salt water which would be moving down, and these pockets would be occupied by air, or you have gas plugs or gas bubbles which would occupy these pockets in the ice, and this salt water would slowly percolate down. Now this salt water would be percolating towards the polar seas or polar regions, and there would be a kind of internal circulation from poles to equator. So if I draw a diagram here, so we understand what is brine rejection now, and this brine would slowly and gradually move down towards the base of the ocean because of high salinity and lower freezing temperature. They would kind of move down. When they move down, you have the earth here. So this is 90 degrees and this is 0 degree equator. So this brine which is settling down here would slowly and gradually try to move towards the equator, and this whole ocean bottom would kind of maintain a common temperature which will be around 0 degrees to 4 degrees Celsius, okay, and this is maintained by kind of circulations which are present here. So in this slide we can understand further what is brine rejection. So you have the ice layer that we can see here, okay, then you have pockets of brine which are present, and this brine kind of subside down, and there is higher salinity in the lower waters, okay, and from here you have gas bubbles through which you have the sensible heat or the heat that comes out, okay. So what is happening is you have a diagram here that shows 0 degree as equator, and you have the north and the south poles. So you have ice that freezes here on the north and the south pole, okay. So you have ice freezing here on the north and the south pole, and brine rejection that takes place, and this salt slowly goes down, and there is kind of convection currents or kind of circulations that are maintained in the within the lower waters or the deep waters of the earth, which try to keep the temperature constant. So as you can see, this line shows a temperature of 3 degrees, okay, and this line shows a temperature of 4 degrees that is maintained across from poles to the equator. And this is how the deep sea layer maintains a kind of very uniform temperature with a very less range of variations from around 0 degrees to 4 degrees, and a kind of constant temperature that we can see here. So again in this diagram, we'll move to the same diagram again for ocean depth temperature changes. So in this diagram, we can see you have the deep ocean waters which have temperature around 4 to 2 degrees, more or less the variation is here, okay. So you can see the deep ocean water which maintains the similar temperature throughout the year, and that is due to the phenomena of brine rejection and the circulations that operate from poles to equator. So we can understand here what is happening is this layer, due to this concept, would maintain a kind of constant temperature, more or less similar or constant temperature, and there would be a drop in the temperature in the seasonal layer. So what would happen in between is there would be a drastic change in the temperature, and this drastic change in the temperature is the region what we call as thermocline. Okay. So thermocline, again, there are few things that we must know about thermocline. There is around no thermocline in the polar areas. I should say no or negligible thermocline in the polar areas, because for the poles you have a kind of ice on the top, so there is no drastic change in the temperature. So the temperature across the ocean is maintained in a kind of similar fashion. So this diagram, when we talk about, mainly deals with the tropical seas. Okay. Again, you have the permanent thermocline here, and in some regions you have a seasonal thermocline that develops. And this seasonal thermocline which develops is the major zone for flourishing of phytoplanktons. So you have the whole blue sea which will be turning around a green biomass. So you would have a seasonal thermocline in some of the areas in the tropical seas, where you could see a far off patch of ocean which appears much more greener than the remaining region in kind of spring months or specific months, and that is due to the growth of phytoplanktons, and that is very seasonal in nature. And this seasonal layer comes and goes, while this is the permanent thermocline layer that is always there, and this layer has a steep change or a drastic change or drop in temperature. So here is a final graph that we were trying to understand. So you have three curves here. The first curve talks about temperature, the next curve talks about the salinity, and the final curve talks about the density. Okay, so you have the temperature here, as we have already seen, This is the surface and the mixed layers. Then you have the thermocline and the deep ocean waters where you have a kind of circulation. So we can broadly say the upper layers are governed by radiation. The middle layers or the mixed layers is governed by waves and winds or ocean currents, and the final layer that is governed by convection or circulations within the ocean from poles to equator. As we can see here, you have temperature that increases as we go deeper into the ocean. We have already understood the concept why the salt slowly percolates down, because water which is much more saltier would have a higher density, and because of higher density it would kind of try to move down. So you have the curve of salinity which is increasing with the ocean depth, and finally you have a curve of density which is governed by a function of temperature and salinity. By these two, you have the density that comes out, and you have a final curve of density here. We would be talking more about salinity and ocean currents and waves in the further classes. To know more on that, you can subscribe to Examrace channel. Till then, have a good day ahead.